Hi engineers, this is Mrs. J. Today we're going to look at centroids. Centroids is coming up at the end of the week or the beginning of next week, and we're going to look at how to find the center of an object. So we have a few things to do before we can look into it, so I want to give you an intro to that. So when you're finding a centroid of a shape, something that's like a circle or a square, it's very straightforward. However, for an object such as a beam, the centroid is only represented by the geometric center if the material is uniform or homogeneous. Beams and other materials are often reinforced with a different material. Such reinforcement likely changes the location of the centroid from the geometric center. It's important that engineers account for those in their designs. So we're going to figure out what they're talking about here before we go and find the centroid. So first off, let's take a look at what a beam is when we're talking about beams. So in construction, we use beams. See that design there? It almost has an eye shape. If you put it straight in front of your face or cut it in half and took a look at it, you can see how they're cut in here. So it's almost like the letter I if you were to cut this off, right? So these are the type of beams we're talking about. When we get into centroids, I'll show you what they mean by having a circle. It's really simple. You're really just looking for the center. Super simple. But these have like odd shapes, like see there. So we need to find the center of it so we know where the weight or the load can be placed so it doesn't collapse. So that's what we're going to be looking at, how to calculate the centroid in each of these objects. It's pretty straightforward. It's actually pretty fun to do. And then we have some software to use to help us along on that. So that'll be later in the week. You'll need to know that a centroid, this is a definition, the centroid of a plane 2D, two-dimensional figure, or a 3D solid figure is the geometric center of the object. You'll remember from IED class last year that a 2D sketch is just flat on paper, and a 3D solid is one that's been extruded. So let me see if I have a 2D image. Probably don't have a 2D image. Well, we're going to see one next week, but it's literally just the letter I. And that's like 2D flat. If you write the letter I on a paper like that, flat on a paper, this is not the letter I, but it's flat, as opposed to it sticking out like these. Where'd the other ones go? So as you see how these come straight out for you, as if you made this an inventor and you extruded it. That first flat sketch is 2D, and then when you extrude it, it's 3D, and these are 3D. So we show how we can do the math on the 2D part because it's easier. That's what we're going to do. So the reason I bring this up is because I need you to get some materials around your house. Cork board, poster board, cardstock. You can skip the cork board. It was for us to plug a thumbtack in. We'll do that in the classroom. At home, you could just tape it to the wall or tape it to the refrigerator. We'll use some, you need some Scotch tape. Poster board or cardstock, actually the easiest thing to use is an old Amazon box. So if you get an Amazon box delivered, keep it. You're just going to make a couple of shapes. You're going to cut them out. Thick paper works too, but it's going to be really thick, like the back of a spiral notebook. Or what else? Like a greeting card, but it's got to be large enough that you don't have the fold of the greeting card in it because that'll throw it off. So your best bet is a nice big Amazon box. You can do that. Also, those really thick envelopes that come in the mail with like Amazon packages that are brown, they're fairly okay. They're a little flimsy, but they'd be okay. When it says paper, 20-pound weight or less, it is just regular notebook paper. We're going to take notes. Some tape to hold it up and a little piece of string. If you don't have any string, you can use some floss if you're not using those little flossers, the long floss, something to hang it up. So we're gonna cut the cardboard, make a shape, and then we're going to hang a piece of string across it and see where the center is. And it's kind of fun. Okay, so before we can do all that, we need to look at the intro to statics, and that's going to be our lesson for today. So what I just talked about there was for you to find materials, cardboard, string, tape, for some time next week, or later this week, early next week. So we're going to look at statics first. We took a quick look at it last week. Let me open that up for you. Okay, so statics, and this is Project Lead the Way, Principles of Engineering. We're looking at solid bodies. And we have a lot to look at here. There's a lot to go through. Great instruction here. You'll enjoy this a lot when you're in college. You get to do some really good labs with this. So statics, and you'll want to take a few notes here. It's the basis for studying the study of engineering mechanics, specifically rigid bodies, which is a solid body. You can pause this and write this down, but it's a solid body in which the deformation is 0 or so small that it can be neglected. That is, the body remains exactly the same size and shape regardless of the forces exerted on it. Meaning those beams we were looking at, say you put an elephant on the beam, you're probably not going to see the beam bend, although it might be bending, but you can't really tell. Or when the elephant gets off, it goes back to normal, so you can ignore it, but you need to know it's there. And that's what they're talking about. So deformation is a change, and it either goes back to the way it was when the force is off of it. So you're building something and it changes a little bit. When you get that stress off of it, it goes back to normal, or you can't really tell. That's what they're talking about. And then mechanics is a branch of physics, and that deals with the motion of objects at a large scale. I know we think of mechanics as cars and trucks and boats and planes, but it really is just the part of physics that looks at how things move. So large scale, right? Okay. So we looked at that last week for a minute. We also looked at Newton's first law, second law, and third law. We got a good look to see how on the first law, something that's, not moving will continue to not move unless something makes it move. Or if something is going and it's moving, it stops because something gets in its way. So there's a force either starting it or stopping it. We looked at the second law. We looked at how acceleration is proportional to what happens to it. And it's inversely proportional to its mass, meaning something heavy is going to be harder to move than something light, right? And then for the third law, we looked at opposite. Everyone loves this one. There's an equal and opposite reaction force. So we enjoy this a lot. You were working with a partner to make a flip grid to describe and demonstrate one of these laws. So given that you spent some time talking to a partner or just thinking about what one of these laws would mean, you should be able to go back, and you pause the video now, and you're going to go back to this lesson in Google Classroom. It was Newton's coolest cool chart. See if I can get it to load. Most of you understood the instructions very well. Some of you are already done with this. That's great. You don't have to do anything. But on the third slide, I needed you to put in 2 statements of what you knew about Newton's laws. And you should have heard this before. You should have heard it in elementary, maybe later in middle school, but you should have been familiar a little bit. If not, I hope you looked it up a little bit. 2 things you knew about Newton's laws. And then we watched some videos, right? They're right here on the first page. We watched a couple of videos in class. And then here we wanted to put in 2 things you wanted to know, and something that might be important about Newton's laws, or what's new, what can I learn about it. And now that you've spent some time with a partner and some time on your own and you've made your videos, what did you learn? And it can be simplistic. You don't have to put an entire formula here, but it should take consideration into what you learned. So put a little effort into that. And it needs to be 2 for each of the columns, and then I'll give you the grade on those. So you can pause now and go fix that. Okay, if you paused and came back, you know that we were looking at statics. We looked at Newton's already, and now we're going to look at more detail. So you'll need to take a little bit of notes here. We're going to look at equilibrium. We looked briefly at equilibrium when we looked at the levers. Sorry, I couldn't think of what their name was. When we looked at levers in the beginning of the year, we looked at the moments on either side of the levers and what was missing, how to balance those levers. So here it says, in science, equilibrium refers to a state of balance. A system is in balance if a system stays the same. It may stay the same because nothing is influencing it or the influences are in balance. There are many forms of equilibrium. We can have thermal, chemical, economic. For statics, we're concerned with the equilibrium of bodies that are in a state of rest or uniform motion. So they're either holding perfectly still or they're continuing to move at a steady rate, constantly moving like a machine. Okay, so we have static equilibrium, and we've got some definitions we need to put down. This is the same as that, so I'm just going to read here. And you want to pause, put this in your notes, please. Static equilibrium is a condition where there is not a net external force acting upon a particle or rigid body, and the body remains at rest or continues at a constant velocity. That is, when force is acting on an object that is at rest or balanced, then the object is a state of static equilibrium. So think of a lever like a seesaw, kids going up and down on one side. If they get it to balance perfectly and it's not moving, that's equilibrium. To be in static equilibrium, the object must be in both translational equilibrium and rotational equilibrium. And we'll talk about that next. So it's also static equilibrium when that same seesaw example is going up and down. Say you've got a machine making it go up and down at a constant rate. That's the same thing because it's going at a constant rate. It's not changing, constant velocity. Okay, translational equilibrium. Remember to pause the video to get the formulas and the definitions. So translational equilibrium is a state in which there are no unbalanced forces acting on a body. So the sum of f of x is equal to 0, and the sum of f of y is equal to 0. And we'll look at this math later, but that's how you read those. Here is a truss bridge, and we're going to build these out of balsa wood so we can stress them, see where they break. This is balanced, translational equilibrium. There's nothing acting on here. There's no cars, no trucks, no wind. We're assuming, right? We're assuming. Nothing making this have any issues. This one, if they didn't do the math correctly, meaning they didn't account for how many trusses they needed, and the triangle is the truss, and we'll talk about that later. Each member pulls its own weight. If you don't do the math correctly and you put stress on it, it's unbalanced and it could fracture, break, or collapse like it did here. For rotational equilibrium, here's the levers I was talking about. This is the state in which the sum of all the clockwise moments, so clockwise, that's blue, equals the sum of all the counterclockwise moments about a pivot points, that's the red. So let's remember what moments are. We haven't seen these since the beginning of the year. Was that not going to work? Come on, you. Nope, not going to work. Oh, okay, I'll add that in for you later. Oh, I got a picture for you. Let's see if I can get it. No. Well, the moment is when we looked at, if you remember from the beginning of the year, force times distance. So we looked at either side, left and right, and we looked at how much force, so these blocks, times how far away, the distance they are from the fulcrum. And then we looked on the other side, the ball, how much weight it has, or the force here, and how the distance is. So moment equals force times distance. They're saying here the sum of the moments, so this side and that side, would be equal to 0. We've already done the math on this. We'll revisit it and it'll be fresh in your head again. That's pretty easy. Okay, so let's look at static equilibrium force principles. Make sure you're taking notes, pausing the video, and adding the diagrams as well as the definitions. When a system is in static equilibrium, forces always occur in pairs. We like this. Force pairs act in opposite directions and have the same magnitude. Oh, it looks like my definitions have run away from me. Let's see if I can get Inkling to populate itself again. Forgive me, it's easier to reload than to. Nope, not going to do it. Magnitude is how much something is happening to your objects. So, for example, if you sit in a chair, you put a force that's equal to how much you weigh on the chair. So if you weigh 100 pounds, you sit in the chair, there's 100 pounds of force pushing down on the chair. And the chair exerts an equal and opposite force on you, supporting your weight to keep you from falling on the floor. So let's use these arrows before we look at the picture. This is you, 100 pounds, sitting, and this is the chair pushing back 100 pounds. So you're not sitting on the floor because that chair can handle it. 100 pounds there, 100 pounds up, everybody's happy. We like that. That's static equilibrium because your chair did not collapse. Same amount of force. How much? 100 pounds here, 100 pounds there. How much? That's magnitude. If an object is in equilibrium, then the forces acting on the object are balanced. It's important to note that balanced is the key word, and this concept can be drawn from Newton's first law of motion. Remember, it said an object in equilibrium is at rest or staying at rest, or in motion and maintaining a constant velocity. Constant velocity means that it's just continuing to move the way it is without changing. It's not speeding up and slowing down, or getting going too quick or too slow. It's staying the same rate that it's moving. So here's a question for you. After a bridge collapses and comes to rest, is it in static equilibrium? Why or why not? We're going to come back and revisit this at a later date. And remember, can you use that bridge if it collapses? We'll come back to that later. So let's look at forces. What's a force? A force is pushing or pulling an interaction of objects. It's a vector quantity, so it's always defined by magnitude. Let's see if it works this time. Oh, there you go. The absolute value of a number, or the easy one, how much? So it has a magnitude and a direction. So how much and how far? That's what we want to know. Two things. Two things is what makes something a vector. So you're probably seeing vectors in your math class right now. Remember, it always has two things, the number, the absolute value, and it has a direction. Which way is it going? Here's an example. A 100-pound person sitting in a chair, like we just saw in the picture, exerts a force 100 pounds downward towards the center of the earth on that chair. So that is two things. That's 100 pounds of force, and it's going in the downward direction. So we go back up to our friend here. 100 pounds going down. That's a vector. Two things, a number and a direction. So now let's look at a vector. We represent vector quantities with directed line segments. We use arrows. The arrow means that it's a vector. If it's just a line, it's not necessarily a vector, but an arrow indicates a vector. The length of the line segment represents the magnitude of the force, or how much, and the arrowhead indicates the direction of the force, or which, how far it's going. So vector, it's got two parts, right? Vector has both magnitude and direction, how much and how far. So make sure you're putting all of these in your notes. I know I'm talking fast, but I don't want the video to be long, so pause and write. And I'll hold that a second. So you can pause. And we'll look at the picture. Here's a vector. We have a green arrow, and it is going, it has 45 pounds of force, and it's going in a northeast direction. So remember your compass, north, south, east, west. It's going northeast. Or I could say 45 pounds to the right. It's going to the right, up and to the right, right? So as long as I have two things, I'm good. So for units, Project Lead the Way stays with our pound force units, or the British system of units, pound force. We can say that 1 pound of force is equal to 4.448 newtons. And the international system of units, we could say 1 newton is equal to 0.2248 pound force. And you'll have this on your keys for your exam, so you don't have to memorize that, but you know where you can find it. Okay, so what's a moment? We're almost done here. Last thing we're looking at. We looked at this when we looked at levers in the beginning of the year. A moment is the tendency or force to rotate on an object. This is caused by a force acting on an object at some distance from a fixed point or axis. To fully describe a moment, you must know the magnitude and the direction of the moment. So let's look at little Mr. Penguin here on his diving board. He's being fancy. The weight of the penguin, so let's say he weighs about 20 pounds, will try to rotate the diving board about its support point. So just like a lever, there's a fulcrum here, and then he's this far away. So we could do the moment, right? Force, 20 pounds, times distance, he looks to be about 3 feet. So you could say the moment is equal to his 20 pounds times 3 feet. By him standing here, it's got to bend a little bit, you know, maybe, you know, bend a little bit so he can hop off. Or maybe it's really sturdy. We don't know, but we can do the math on that. Okay, that's it for today. There's going to be 2 questions in Google Classroom for you to answer, and then you'll be done. Thanks so much.